Sand. It gets everywhere. As Manny would say, for a mammoth, you're not very big. And for a box of sand, we're about to create some geological drama with faults and folds. All of our very limited knowledge comes from the greatest film of all time.
This approach is highly valued in the attempt to understand complex structures that are otherwise challenging to study and bridges the gap between theoretical concept and observable phenomena, allowing us to interpret and predict Earth's structural behaviours. In the 1800s, a lateral compression machine was used to mimic folding in clay that was seen in an outcrop. This has then further been developed by numerous scientists such as King Hubbard, who introduced scaling.
Faults are a discontinuity formed by fractures in the rock surface when tectonic forces exceed the resistance of the rock's principal stress. There are three principal stresses. Sigma 1 is the maximum stress. For a normal fault, this would be vertical. Sigma 2 is the intermediate stress, and Sigma 3 is the minimum stress and is in a horizontal motion for a normal fault. These forces could be seen in our experiments later in the video. There are two types of faults that could potentially be seen in the Sandbox experiment: normal faulting and thrust faulting. However, thrust faulting is much more likely. Both of these are seen in the Zagros mountain range in southwest Iran, with the oldest rocks being dated at 541 million years ago.
We use sand in the Sandbox models for one simple reason. It's easily deformable. We can push and compress it, simulating continental drift, as it simulates brittle upper crust faulting. Water can be added to the sand to increase cohesion and increase effective stress, therefore creating a more realistic environment in the Sandbox. But sand doesn't come without its limitations. It's non-cohesive and is heavily affected by friction from the floors and walls, lowering the accuracy of our results.
Sandbox modelling lets us visualise complex geological processes. We can see how faults and folds form, how mountains rise, all in a controlled environment. We can even scale it up, from tiny faults to entire mountain ranges. It's a great way to recreate real-world scenarios. But it's not perfect. It's very simple after all. Rocks aren't just sand. Crucial factors like rock properties, fluid pressure and temperature aren't included, plus human error is common. Measuring things precisely in sand is tricky, and let's face it, every Sandbox experiment is going to be a little bit different.
See this white powder? And no, it's not what you find at the gardens at Astoria, it's talc. This can create the colmont, which is not a fancy French dessert. They are a crucial part of creating mountain ranges such as the Himalayas and Zagros mountain range. Deformation like this is often referred to as thin-skin tectonics. They are most commonly associated with thrust faults, where layers are thrusted over each other at a low angle of 30 degrees. Overall, talc acts as a lubricant which reduces the effects of friction across the layers and also against the edge of the box, which will increase the accuracy of our experiments.
For our experiment, we created two sandboxes of equal thickness at 3.5 centimetres. Our first experiment will involve 2 layers of wet sand and 2 layers of dry sand, with millimetre thin layers of talc in between the layers. The second experiment had a 40 centimetre total length and once again had layers of wet and dry sand. These should be able to effectively test our hypothesis and recreate the Zagros mountain range. In the first Sandbox experiment with 2 layers of talc, the box experienced 18 centimetres of shortening before the final wedge reached the end of the box. After 4 centimetres of shortening, 3 faults were formed, causing a very small second wedge. However, this will eventually be removed by the original wedge. After this, a thrust fault occurred, causing a décollement, which would likely be due to the talc reducing the friction between the sand layers. The hanging wall thrusts above the footwall, which keeps its place. At 14 centimetres of shortening, a second fault occurred, causing another décollement. This led to the middle block of sediment thrusting over the final block, causing a large second wedge that is pushed through and over the other sediment. We saw a total of 11 faults formed, with the average angle of the youngest fault being at 31 degrees.
The second experiment had no talc involved, with the black layers still being wet sand. We attempted to keep the layers the same size with a total thickness of 3.5 centimetres. Having no talc made a huge reduction in the amount of faults, with only 5 being seen across this experiment, and 11 in the first experiment. The first fault was formed at 2 centimetres of shortening, with the next 2 forming at 10 centimetres. Thrust faulting then caused a décollement of 14 centimetres of shortening, which happened much later than the previous experiment due to the increase in friction between the wet and the dry sand.
The first experiment conducted with 2 layers of talc showed over double the amount of faults compared to the second experiment. This is a huge difference caused by the reduction amount of friction between layers of wet and dry sand.
Having wet sand and talc gave experiment more realism as seen in the Zagros Mountains. However, the talc doesn't remove all of the friction in the experiment, as sand was still lost underneath and to the sides of the pushing block, which wouldn't happen in a real-life setting. One issue with our experiment was that the water from wet sand leaked into the other layers, causing a large amount of the layers to be wet, therefore increasing cohesive behaviour between the grains. When comparing the faults between experiments, it was represented through our results that experiment 1, containing talc, produced a larger number of faults due to a reduction in friction. After 20 centimetres of shortening, there was 11 faults in experiment 1 and only 4 faults were visible at the same distance of shortening in experiment 2. Through both experiments, the youngest fault averaged around 30 degrees, which is in line with what we predicted for our thrust fault angles.
The average dip of the top surface was significantly larger in experiment 2 than experiment 1. This could be due to talc acting as a lubricant, causing a reduction in internal friction, allowing material to slide over it more easily.
I don't like sand. It's coarse and rough and irritating, and it gets everywhere.